Bello. Thanks for this opportunity to present at the DCASE 2021 workshop. The title of this project is micarraylib, Software for Aggregation of Microphone Array Datasets, co-authored by me, Iran Roman, postdoc at NYU's Music and Audio Research Lab, and Professor Juan Bello. In recent years, machine listening has seen major advances for sound event detection, including the recent audio spectrogram transformer, AST for short, which achieved state-of-the-art performance in tasks like audio classification, audio tagging, and keyword spotting. Models like the AST are possible thanks to datasets like Datasets, which have millions of clips with annotated sound events. In our lab, we're interested in the related but different problem of sound event localization and detection, which usually requires the identification of a sound event's label, but also its location in space. On the bottom right, you can see an example of such scenario where a microphone with multiple capsules, known as a microphone array, is listening objects in space that can be stationary or moving. To develop models as robust as the AST, large amounts of microphone array recordings with annotated spatial events will be necessary. We have surveyed the datasets available online that include recordings with microphone arrays, and we have found over 30 that could be useful to develop models for sound event location and detection. However, these datasets have been captured with different hardware. Examples of hardware can be as diverse as the Sennheiser Ambio microphone, which has 4 capsules, but also exist some homebrewed arrays like the Pyramid array that has 48 capsules. This hardware diversity makes it difficult to combine these datasets. We decided to focus on a subset of popular datasets to design a method to aggregate them. These datasets include the DCASE Task 3 Challenge datasets from 2019 all the way to 2020, all with one array and sound event location and detection labels. But also we included the Locata, 3D Marco, and Eigenscape datasets, some of which don't even have notations, but are collected with a more diverse set of microphone array hardware. If aggregated, these datasets combined would give about 50 hours total of useful data for sound event location and detection. The main issues making aggregation of recordings across these datasets difficult are the different hardware used and the different conventions in sound event location and detection annotations. As a solution, we proposed standardizing recordings and annotations. The recordings can be converted into ambisonic XP format using a generalized encoder, while the sound events can be parsed to fit the sound data library spatial event attributes, which include object label and unique number identifier in each recording, location, and the times of incidence. Sound data is a library that I have contributed to, and you can already use it in its pre-release form. In this work, though, we present micarraylib, which allows users to access microphone array datasets in original and also in standardized formats through that ambisonics encoder. How does micarraylib work? We load the microphone array capsule coordinate information, and we use it to compute the real valued Laplace spherical harmonics matrix using the coordinate information in this equation that you see on the screen. We then use the pseudo-inverse of this matrix to multiply the raw recordings and obtain a simple ambisonics encoder. While more sophisticated encoders exist for perceptual purposes, this simple encoder is one that can capture spatial information in ambisonic XP format and is useful for machine listening purposes. Using micarraylib is as simple as creating a list with the objects of the dataset supported, loading them, and using micarraylib's aggregator to encode all clips in ambisonic XP format with their respective annotations. With the dataset supported so far, you can obtain a sizable amount of data in first order ambisonics with a good chunk of annotations, as an example. We created micarraylib because we want to use it ourselves to aggregate datasets and then come up with experiments and models that have more useful functionalities. As an example of a use case, we have experimented with virtual capsule interpolation of microphone arrays. We asked the question, can a microphone's capsule recording be reconstructed using other neighboring capsules? We hypothesized that such reconstruction is possible using the capsule recordings and space coordinates. We have focused on using eigenmic data. Eigenmic is a specific microphone array that is very popular, and you can see it here on screen. And some datasets that include eigenmic data are the Eigenscape, the 3D Marco, and Locata datasets. For this, so we skipped the encoding step and we kept the recordings in a format because we wanted to work with the capsule recordings. To capture the space info in these recordings, we decided to use an intermediate step between the A and the B format as input to a Linnet architecture. We still compute the spherical harmonics matrix, but we multiply the samples recorded by the corresponding capsule with these coefficients without doing the linear combination that would be necessary to do the encoder. In that way, what we have is a matrix where the samples for each capsule multiply the coefficients of the spherical harmonics. A capsule samples are missing in this matrix, and the task of the Linnet architecture is to reconstruct it using the information of all the other capsules. We did 3 experiments with this input data. In one, the information or the recording of a single capsule is missing. In 2, we also remove 5 neighboring capsules, not just the capsule we want to reconstruct, but also its neighbors. So for example, if we wanted to reconstruct 1, we will remove 5 of these 6 around. And then in another experiment, the input only has samples of 3 capsules that will result in a tetrahedral shape with respect to the capsule we want to reconstruct. The results that we obtained in this experiment show that before training, the Linnet architecture had a mean square error at the sample level of reconstruction of 0.9, and then that error was reduced in experiment 1, 2, and 3, but to a lesser extent in experiments where more capsules were missing in the input data. This shows the usefulness and the need for micarraylib to be able to combine data sets, but also shows that the reconstruction of these capsule information is possible, but sensitive to physical and density information of the recordings available to reconstruct. In this plot, we show the activation in the first CNN layer, which in the center would correspond to the missing capsule information, and then you can see how the output of the CNN is using the neighboring information to reconstruct everything. Some closing thoughts for our project are that the work so far and more that we're working on are available online. We're open for collaboration, discussion, and suggestions, and we also will continue adding data sets and microphone array hardware as we need it for our research. We also will continue experimenting with the virtual capsule interpolation methods, and we hope that this can be added as a data augmentation tool for micarraylib. We want to thank NYU, our funding sources, our research lab, and also you for listening. Here are some of the references that we have cited. Thank you.